So happy Monday, everyone. Anyone have any questions about assignment 1? Exciting assignment 1 before we start? I'm actually picking up a signal. I'd like to practice my psychic powers. I'm picking up a signal from the class that some of you do have a question that you're too afraid to ask. It's okay, because I can read your minds. You don't even have to say anything. Some of you are wondering, what about the assessment sheet? Is that available for us to see how it's going to get scored and how it's going to get marked and all that stuff? Am I right? Were some of you thinking that? I think some of you were thinking that. The assessment sheet is on Blackboard. So you can go on Blackboard and click on assignment 1 and then find out exactly how the points are allocated on assignment 1 and how many points each part is worth and all that stuff. Yeah. Sound good? I like the excitement. I like the excitement. This is an attendance register. Everybody could sign. Okay, if there are any questions or comments, feel free to interrupt anytime. The Monday noontime excitement is electrifying the room. So you might remember last time we talked about a little bit about data dimensionality, or at least we introduced this concept. We're going to keep talking about it today. We discussed data characteristics a little bit. This is going to be a recurring theme throughout the module. And this is what most people associate with data visualization, presentation. This is the part when, after your analysis and exploration of the data is finished, you use visualization to communicate the results to an audience that might not be specialized. So we always have to ask ourselves, how can the data be presented? Is it scientific data? In other words, does it have an inherent spatial domain? In other words, does it live in a 3D or 2D space that corresponds with nature somehow, or the real world somehow? If that's true, should we use that same domain to present the data? If not, then what else? What are the alternatives? Are there some other space we can use to present the data? And which dimensions are used for which purpose? Right? Whenever we have a dimension in presentation space, it has a purpose. It has a mapping, a visual mapping, an x-axis, a y-axis, a z-axis. And what are those used for? And what is the relationship between the data dimensionality, the presentation dimensionality, and the data characteristics? Generally speaking, we have a 2D plane to project our visual designs onto, like this slide right here. We could use 3D space as well. So 3D space usually looks like a cube that can be rotated and viewed from different angles and zoomed in and out. You're going to see that more on assignment 2, by the way, if you're interested. And then there's 4-dimensional space. Anybody know what 4-dimensional space is? Can anybody remember from last Monday? Name?
John.
John?
John.
Joe.
3 spatial dimensions plus time.
Awesome, Joe. Thank you. Thank you. Joe is awake. So it's 3D plus time. So that could take on the form of an animation, for example. This is also a very important question. Where is the focus? So not all data has the same level of importance. Some data is more important than other data, and that implies that some parts receive special focus while other parts receive less focus. And then we have this other kind of question, related question, what can be left out? Is there some subset of the data that can be left out because it's not as important? So these are some examples, right? And we're going to try, these are examples of different data dimensions. So I'll try to explain this. So this n means any kind of data, for example, nominal data, right? And this 1 means to the first power, so nominal data, 1D nominal data, so one-dimensional nominal data. For example, a histogram of exam scores, right? This is a histogram of exam scores. And those exam scores can be mapped to a one-dimensional height. So the R means real numbers, the set of real numbers, and the first power to the first power means one-dimensional. So any nominal value can be mapped to any height, right? That's what this symbol means. This is the mapped to symbol. By the way, that arrow means mapped to. And I think everybody in this room has seen bar charts before and histograms. So that's just an example, right? So these are all examples: bar charts, pie charts, histograms, bubble charts. So any one-dimensional value can be mapped to any one-dimensional space. In this case, it's the height of a bar. In this case, it's a radius, the radius of a circle. So one-dimensional data being mapped to one-dimensional visual space. This is a one-dimensional value being mapped to a two-dimensional visual space. So for example, an amplitude, a time series amplitude is being mapped to a y-axis and an x-axis. That's what the R square is. Right? The R1 just means a set of numbers or a set of real numbers being mapped to a 2D space. And an example is a graph. In this example, this is a focus region here, and then that's been blown up and shown in a zoomed-in view here. So that's also an example of some data being more important than other data. Here's an example of two-dimensional data. That's what the R2 stands for, a set of real numbers being mapped to two-dimensional space again. So the previous example was also two-dimensional space. In this case, it's a set of two-dimensional vectors. So vectors have, as we remember from last Monday, an x component and a y component. And those x and y components can be mapped to these two-dimensional glyphs, right, along an x-axis and a y-axis. So the same can be said about texture-based methods. So those are glyphs. This is a texture-based flow visualization method based on textures, which we'll talk about later on in the module. I am a little bit cheating or lying here. I've also put this R3 in brackets. Anybody feeling really ambitious and wants to explain why I put R3? Remember, this is the presentation mapping. So here I'm saying two-dimensional numbers are being mapped to two-dimensional space or presentation space. And then I have a third dimension in brackets in the presentation space. Wow, good. Some people are awake. What's your name?
Alex.
Alex.
Is the third
Awesome, Alex. Awesome. It's so nice to know that there are people alive in the audience. Yes, yes. That R3 is color. So I should have used like black and white here if I wanted to keep the R2 to R2. So the third visual dimension there is color. Same here. I cheated. This color bar gives it away, by the way. So there's an x-axis in the presentation space, a y-axis, and then there's a color. So those are the three.
Just a quick question.
Yep.
Is that not four-dimensional because you've got x, y, directionality, and intensity?
That is confusing. So, what's your name again?
Joseph.
Joseph asked, is that not four-dimensional because you have x, y, a direction, and then color? The answer is the direction is defined by the x and y. So for a vector, you break it down into an x component and a y component. So that's why we say it's just two. So that third one is kind of derived, let's say. Any other questions about that? This is confusing, by the way.
Sorry.
Yep.
You said you could have used black and white, but like
yep.
Grayscale is still like.
That's why I said black and white and not grayscale. Good observation, though.
If you use two colors, then that's still.
Yep. Arguably, what I was thinking when I said that was a white background and then black glyphs. That's why I said that. But good observation. What's your name?
Joe.
Joe. Very good. Yes. I almost said grayscale. I think we had a psychic exercise there because I almost said grayscale and then I held my lips back, took a deep breath, and said black and white. If it was grayscale, it would still be R3. Any other questions? You might be asking, like, what am I talking about right now? I'm talking about three things. One is data dimensionality, another is presentation dimensionality, and then the mapping between the two. That we have a data dimensionality, a presentation dimensionality, or a visual mapping dimensionality, and these are not always the same. For example, 1D numbers can get mapped onto a 2D space. 2D numbers can get mapped onto a 3D space. 3D numbers can get mapped onto a 2D space, and we're going over examples. So the message is the data has a dimensionality, the visual mapping or the visualization has a dimensionality, and they don't have to be the same. Name?
Marcelli.
What's your question?
Wouldn't it be the same if instead of arcs we have points of different color? But then we wouldn't have the direction, so isn't it like four-dimensional data?
Yes, that would be true if we had just a scatter plot with an X and a Y. That's true. That's true. It would still be if we just have the X-axis and the Y. The reason I say that that it's 2D here is because every vector has an X component and a Y component, and they add together to generate the direction. So it's like two.
They also have a position.
They do have a position. That's true. That's true. And well, in this case, they're all the same magnitude. So in this case, the magnitude has been stripped away, and they only have a position. They have position, direction, and then the magnitude is encoded in the color. If I wanted to add another dimension, I could vary the length of the vector glyphs so they have different lengths, and then that would add another dimension. Does that make sense? So all of these vector glyphs have the same length, and so something has been taken away from that, and that is the magnitude. But the magnitude is encoded in the color. I don't know how much I should talk about this, but you're right. in the sense that imagine I had these vector glyphs of different length, then we would have two other aspects that you're asking about. The magnitude of the x component and the magnitude of the y component that are both changing. So we would add another 2 dimensions. Yeah, it's a confusing example. I don't want everybody to get too confused. But yes, you're onto something there. Here's an example of 3-dimensional data and three-dimensional space. So this is an example where the vector glyphs are, the magnitude is changing. And they all have, the position is a spatial grid, a polar spatial grid. Here's another example of using 3-dimensional streamlines. So this is vector fields. And here's an example of a stream surface. We haven't said exactly what those things are yet. But a stream line like this is a line that's everywhere tangent to the vector field. That's jumping ahead. We're just showing some examples. I put a 4th dimension in here again, which is that color. That color. And a stream surface, by the way, is a surface that's everywhere tangent to the vector field. And we're going to go over that later, what that means. Here's an example of an arbitrary number of dimensions being mapped to an arbitrary number of spatial dimensions. And this is an example we're going to look at in detail later on in the module. But each one of these axes along y represents some data dimension and a visual mapping dimension. So we can take any set of data, map it on a scale from, say, 0 to 100%, and repeat that process for an arbitrary number of data dimensions and visualization dimensions. And that's actually part of assignment 1, by the way. You can do that in assignment 1. And this is very useful for data that's stored in a spreadsheet that has an arbitrary number of dimensions, like in assignment 1. And this visualization is called parallel coordinates, which we're going to talk about. Another example is glyphs or icons. Everybody's seen glyphs before. Anybody know where they've seen glyphs before? Where's that attendance? The attendance register, is it being passed around somewhere? Okay, good. Has anybody seen glyphs before? Name?
You know that color visualization was hue, saturation, like its value and so on?
Yeah. That's a good example of a color legend or a color space. Anybody here have a driver's license? A lot of people. So you see like glyphs and icons when you get your driver's license. You have to be able to identify like the different symbols that you see along the road, like a stop sign, for example, or that sort of thing. This is a rugby glyph. It represents one event in a rugby game. Right? This is the type of event mapped to a pictogram. This represents the time the event occurred. This is the start time of the game. The thickness represents how long the event lasted. And there were other attributes. 1, 2, 3, 4, 5, 6, 7, 8, 9 data dimensions mapped to 9 visual channels in this rugby glyph, which we're going to see more of in the future. Now, I know that part is very confusing, the data dimensionality to visualization dimensionality. The point is that the data dimensionality and the visualization dimensionality can be different. Like, there is a data dimensionality, there is a visualization dimensionality. They don't have to be the same. Sometimes there's an increase in dimensionality from one to the other, and sometimes there's a decrease. That's the point. Yeah. So we'll talk a little bit about color, because we always use color in our visual designs, or we generally use color. So there's a kind of guideline here, and you'll find lots more guidelines, by the way, in assignment 1 with the visguides.org web exercise, right? That's a collection of guidelines on that website. But here's a guideline. The maximum number of colors to use for categorical data is around 7, plus or minus 2. Now, categorical data, does anybody understand what this term categorical data means? Name? Lou. What would you say, Lou?
Well, it's like when you've got a number of, I guess sports is like an example, like football, rugby, tennis.
That's right, that's right. So any number of groups. Yeah. So if you have data that fits into discrete set of groups, like we're supposed to classify students into groups or categories, right? Distinction level, 2.1, 2.2, 3, and all that stuff. Yeah. That's categorical data. That's as opposed to continuous data that doesn't have to fit in a category. For example, all the numbers between 0 and 100%, right? That's continuous data. The human visual system can distinguish 50 to 300 color shades. Anybody here have like an artist background, or have took an artistry or painting class or anything like that? No? Good. One of my brothers has a degree in art, in painting, and I remember one of his courseworks was to create something like 200 to 300 different colors. Like, here's a set of paints, I don't know, maybe 7 paints or something like that. Create 200 to 300 colors out of these paints. And at the time, I thought it was really interesting. Color perception depends strongly on context. We'll talk about this, the rainbow color map that comes up all the time. So the color you see depends, or the color, let's say the color you perceive depends on the colors that surround it. Not only the colors that surround it, but the colors you saw before you saw that color also play a role. Does anybody remember this this funny graphic that went around that was like the gold dress or the gray dress, I think it was? Does everybody remember that? And some people would look at it and say, oh, it's the color gold.
Golden blue.
Golden blue, yeah. And some people would look at it and say, oh, it's definitely a blue dress. And it's very strange. And sometimes you can stare at it and it changes color, right? Did anybody like stare at that dress for a while? I certainly did. It's because of this that color perception depends also on context. So the color of the dress depends on the colors around the dress and what you looked at before you looked at the dress. Yeah. Some users are colorblind and some colors have associations. I think everybody knows that. And some clever student already mentioned this tool. There's a website called Color Brewer that recommends color maps for your visual designs, and it's very useful and it's very popular, and you're welcome to use it. Here's an example of the color of something depending on the context. It's a little bit difficult to see because there's a lot of light here. I don't know if I can't turn off the lights, right? It's not possible. I tried last time. I failed. But this would be better if I could turn off the lights. Why should I be able to turn off the light? That wouldn't make any sense. Like, it shouldn't work. It shouldn't work with the switch. Oh, maybe. So these colors, does anybody see anything there when they look at those colors? For example, if you look at this rectangle, is the color uniform or does it change? Does it have a gradient? Raise your hand if you look at this rectangle and you see a gradient. In other words, the color is changing when you look at that thing. Who sees a constant color, a color that doesn't change and it's completely uniform? Okay, so something like half and half-ish.
That's how it's changing.
It looks, to me, it looks like it's changing. Like if I look at this rectangle, it looks lighter over here, and then it gets darker as I move across. That's what it looks like to me. But in reality, it's actually a uniform color in reality, because the color that you see here depends on the neighboring colors. Because this one is darker or some other shade, the human visual system increases the contrast. And same here. This one looks darker because it's next to a lighter color. And because of that context, it creates this illusion that the color is changing as we go from left to right. And if you want to like prove that to yourself a little bit, this is not a very perfect exercise, but you know, if you had the slide, now it looks more uniform. Did everybody see that? Anyway, you can Google Mach band effect and you'll see more examples of that. But it's a fun exercise, and the point is the human visual system is very good at identifying boundaries and strengthening boundaries. This is what the human visual system likes to do. And by the way, that is a web page, and that web page might still exist. You're welcome to look that up. Color gamuts. So this is about color and reproducibility and devices that produce color. So different devices are able to produce different sets of colors, and those are called color gamuts. Right, here's an example of a color gamut. So this laptop has a set of colors that it can produce, and what I see on this screen is different than what the colors that are going to be projected by this projector. So the set of colors is going to be different. Right? And that's the reason why printing color is so difficult, and printing photographs is so expensive, because it costs a lot of money to get the colors correct. Grayscale lines are good for boundaries, if you need to introduce boundaries. Avoid dark blue for details and animations. Blue and red don't mix very well. I see this all the time, even from really smart people, and I find it very mysterious. But there are millions and millions of PowerPoint slides with very strange color combinations like red and blue. really, really strange.
There's a really good tool if you search WebAIM, which is a color contrast checker, and you put in your 2 hex codes for your color, and it will tell you whether it meets a minimum accessibility requirement.
Web
AIM.
AIM. I have never heard of that. That's very interesting. So this is for colorblind, possibly colorblind users.
Yeah, I think if you go down to the current features at the bottom.
Contrast and color accessibility. Like this one?
Yeah, I think there's a tool that I can send.
Mm-hmm. Mm-hmm. That looks interesting. Mm-hmm. Okay, we don't talk in depth about color. We just introduce it as a quick topic. You can take classes on just color. It is possible to take one full module just about color. Not at Swansea University probably, but I have seen that before. Any questions about that material? That introductory material? Attendance register went around. Everybody signed the attendance register. Good. Now these, at the end of all the lectures, you'll see recommendations for further reading, by the way. So if you want to learn about any of these topics in more detail, you look at these book chapters or research papers or something like that. This is sort of the first recommended textbook. This is the second recommended textbook. This is another textbook that is very focused on the human visual system. So if you wanted to learn the most about the perception of color, look at the Information, Visualization, Perception for Design book. Good.